Hello everyone, welcome to Physics Fundamental with Thomas Adeoye. In this video, we are going to continue our discussion on quantities, units, and dimensions, focusing more on dimensional analysis. If you haven't watched the first video, I strongly recommend that you do so because we are going to be building on it. Let's get started. So to begin with, what are dimensional constants? These are constants which possess dimensions. They are constants in the sense that they have fixed values. Their values are fixed, but they have dimensions. Okay? Some will be like, is there or are there constants with no dimensions? Yes, if that is your question. The answer is yes. There are constants with no dimensions, and I'll give you an example. An example of a constant with no dimension is a pure number. Pure numbers like 1, 2, 18, minus 5. These constants, they do not have dimensions. Is that begin? They don't have dimensions. So if someone asks you what is the dimension of 2 now, 2 is a dimensionless should I say quantity now? 2 is dimensionless. So if you look at this equation, equation v squared equals to u squared plus 2as. If you watched the last video, I recommend that you do so. When we try to use dimensional analysis to show that this equation is valid, one of the applications of dimensional analysis or dimensions is that we can use dimension to show whether an equation is valid, to check for the validity or otherwise of an equation. So when we try to use dimensional analysis to check or to show whether this equation is valid, we discover that 2 is dimensionless. It does not have dimension, and 2 is a constant because it's just a pure number. But dimensional constants, they are different. They are not dimensionless. They have dimensions, even though they have fixed value. An example of them is a Planck constant, as you can see. So Planck's constant in this formula, E equals to hf. So where h is a Planck constant, f is frequency, and this stands for energy. Okay, so in this formula now, h, which is a Planck's constant, has a dimension. And if you have watched our first video, I think you should be able to do this to find the dimension or derive the dimension of h. Just make h the survey formula, find the dimension of energy and dimension of frequency, then we are done with that. You can try this out and drop your answer in the comment section, or you share on our Facebook page. Another example of a dimensional constant is c. This c, which is the speed of light in a vacuum. Okay, so it is approximately 3 times 10 raised to the power 8 meters per second. The value is fixed. Okay, so another example is g. Okay, capital G, universal gravitational constant. In this formula, the force of attraction F equals to G m1 m2 over r squared. So where F is the force of attraction between two masses m1 and m2, okay, and G is the universal gravitational constant, then this r is the square of the distance between them. So this G, universal gravitational constant, is a dimensional constant. It has dimension, even though its value is fixed. Its value is known to be, I think, 6.674. Yeah, I have it written down. 6.674 times 10 raised to the power minus 11 here. And I think the units, from here, we know what the units should be. It should be Newton. If you make G the Soviet formula, Newton meter squared, then per kilogram squared. So we can say kg raised to the power minus 2. And you can find the dimension of this, I mean, by trying to find what Newton will be. You represent Newton in terms of kilogram. Newton should be kilogram meter per second squared. Okay, so let us move on from here. I have mentioned some examples of dimensional constants. We have Planck's constant, speed of light, universal gravitational constant. Another thing is specific gravity. Yes, it is also a no. Don't let us no. That's not a it's not a dimensional constant. Yeah. So let's just leave it to this. Yes, I wanted to mention more. Epsilon naught. This is permittivity of free space. It has a fixed value. Yes, and another one is mu naught. Mu naught is permeability of free space. Okay, and all this they have values. I mean, they have fixed values. Okay, so the next thing now is dimensional variables. So what are dimensional variables? They are quantities, physical quantities that possess dimensions but do not have a fixed value, unlike dimensional constants, which have dimensions but fixed value. You know, we mentioned speed of light in a vacuum, whose value is approximately 3 times 10 raised to the power 8 meters per second. It has a fixed value. But as for dimensional variable, these are quantities. They have dimensions, but their values it vary. I mean, their values vary. They don't have fixed values. Okay. And examples of them, we have displacement. There is force and there is velocity. Displacement, which is a specific or a specified direction between 2 points, or we can say a straight line distance between 2 points or between 2 positions. Now it has it has a value that can change depending on the scenario, depends on how wide. Okay, one of the things it depends on is how wide the 2 points are. Force applied on a body now can have values that change. So we can't just say, okay, the force acting on this particular body is 6 Newton, and you know, everywhere the force remains 6 Newton. No, it depends on the scenario you are trying to describe. And velocity of a car, or velocity now, the value of velocity depends on what is it that is moving. You know, velocity of electrons now is it depends. You can't just say this is the value that electron, this is the value of the velocity of electron. It depends on the body, the medium through which the electrons are moving. Now, the velocity of your car depends on so many things, or let me say the speed. Speed is not here, but it's one of the examples. The speed at which a car will move or will travel depends on so many things. Depends on the kind of car, depends on the road, depends on traffic and things like that. So these are physical quantities. They have dimensions, but yet they are like their values vary. That's why they are classified under dimensional or as dimensional variables. Okay, and dimension of displacement, we did this last week. Check the video, that of force and velocity. So here we have dimensionless quantities. Okay, as name implies, these are quantities that do not possess dimensions. Yes, they are dimensionless. They don't have dimensions. And one example is angles. Yes, angles don't have dimensions. So although angles have units, please, I want you to note something now. Angles, they have units. So that is, there is a scale, there is a yardstick with which we can measure angles. Okay, you know, angles are measured in degrees, okay, or radians. So they have units. The unit of an angle is it could be degree, or you measure it in radian. Okay, but it does not have dimension. It is dimensionless. So what does this tell us? What this means is that there is a possibility that a particular physical quantity has units, but no dimension. So if I were you, I would just note it down that not all dimensionless quantities are unitless. Do you get that? Not all dimensionless quantities are unitless. That is, a quantity, a physical quantity, we can have a physical quantity that has units but no dimension. Someone is like, is converse true? That is it possible for us to have a physical quantity which has dimension but no unit? No, this is not true. But what you should know is that not all dimensionless quantities are unitless. Okay, so moving on, angle has units but it does not have dimension. Another example is specific gravity. Specific gravity is dimensionless. Okay, another thing is because by formula I can say that the formula of specific gravity, let me try to write something down. Specific gravity, yes, the formula is equals to, it is density of substance is actually given as ratio of density of substance. Let me just write SUB over, sorry for this, over density of water. Yes, so it is ratio of densities. So you can see that it's density over density, so they cancel out. So it does not have it doesn't have dimension. It is dimensionless. Another thing is strain. So strain is the formula for strain. It is extension over original length. And extension is measured in meters. Original length is measured in meters. So it cancels out. So in general, or generally, what we have is that any physical quantity that is a ratio of two quantities of the same dimensions are dimensionless. Okay, I think this is yes. If you have any physical quantity like strain, now strain is a ratio of two quantities with the same dimension. You can see that strain is given as ratio of extension to length, and these two quantities, extension and the original length, they have the same dimension. The dimension of extension is L, capital L. Dimension of length is capital L. So the same dimension on top of each other, so it cancels out. So that makes strain to be dimensionless. Same thing happens to specific gravity. Some will be like, what of angles? Yes, in angles now, you should agree with me that if I have a right angled triangle, if this is theta, so if I'm interested in theta now, or in sine theta will be opposite over that's so capital, opposite over hypotenuse. Okay, so it's like, okay, the length of the opposite side over the length of the hypotenuse side. So it's still length over length. So that's the ratio of two quantities with the same dimension. So if we have quantities like this, they are dimensionless. Another example that is not listed here is mechanical advantage in machine. So mechanical advantage is equals to, I think this is this should be load over effort. Yeah, it is load over effort, okay, or output force over input force. So it is like ratio of output force, that's force, input force, force. So force over force, force and force, they have the same dimensions, so they cancel out. Another thing is velocity ratio, so which is effort distance over load distance. So it's still distance over distance. So all these, they are dimensionless quantities. That is, they are physical quantities and they do not possess dimensions. Okay, and yes, let me try to explain this. Frequency, by definition, frequency, okay, unit of frequency. Frequency is measured in hertz. Okay, we can say hertz. It's measured in hertz. And another unit that we can say frequency is measured in, because frequency is given as the number of cycles per time now. So it is n over t, so where n is the number of cycles. So that's why some people will say, which is correct, that frequency is cycles per seconds. Yes, so you can have it as cycle per seconds. Okay, but what I want you to know is that cycle here is dimensionless. Okay, so that's why the dimension of frequency, its dimension is you know, if we say frequency, the unit is cycles per seconds. Yeah, when you say cycles per seconds, let me just try to make it here. So if you want to write the dimension of frequency now, there's a symbol. It is just 1 over t. I mean, it is just the dimension of time. The seconds, seconds is unit of time, so dimension of time, which is capital T, that comes out. Is because cycles now, they are measured in angles, or is related to angles. The unit of angles are degrees, steradian, and you can see that angles are dimensionless. So cycle is also dimensionless. So that's why, even though frequency is cycles per second, so we can see that cycle is dimensionless, and that's why the dimension of frequency is t raised to the power minus 1. So please take note of that. Let's move on. So this is a very important principle, which is principle of homogeneity of dimensions. Principle of homogeneity of dimensions. And what the principle states is that principle of homogeneity of dimensions states that an equation is dimensionally correct if the dimensions of the various terms on either side of the equations are the same. Okay, so what does this mean, or what is all this that I'm reading? So what this principle is saying is that if I have an equation like this, suppose I have an equation, if this is equation of A plus B equals to C plus D. So according to principle of homogeneity of dimension, each term, this is a term, this is another term, this is another term. Let me call this DE. This is another term. Do not make the mistake of saying that there are 5 terms in this equation. No, there are just 4 terms. This is first term, second, third, and the last one. Okay, so what that principle is saying is that each term now must have the same dimension. That is, dimension of A must be equal to dimension of B. Dimension of B must be equal to dimension of C. Dimension of C must be equal to dimension of this taken together. Is that taken? So, and what is the implication? What that means is that only quantities of the same dimension can be added. Yes. Now, let's try to talk about that. If you have this equation, V equals to U plus AT. Okay? So, if we are to apply, or if we are to check if this equation obeys that principle, let's try to take a look at it. So, and based on the principle, these are 3 terms. So this is first term, this is the second one, and this is the last one, 80 combined, do not forget. Okay, so the dimension of V must be equal to the dimension of U. So, and the dimension of U must be equal to the dimension of AT. Okay, so if we are to check that, let me try to check that here. The dimension of U is U is meters per seconds. This is a unit, rather, okay? And we can say that the dimension will be, for meter, it's L raised to the power minus 1. And you should agree with me that for V, we have the same thing. U is just initial velocity. This is just final velocity. It's still velocity. So another one that we need to check is AT. Let's check dimension of AT. So for 80, so we know that the dimension unit of A acceleration is meters per second squared. So, and that can be L t raised to power minus 2, right? Multiplied by, for T is just capital T, which is t raised to power 1, we can say. So if you do this well, this should be minus 2 plus 1, and that should be L t raised to power minus 1. So you can see that this and this, they have the same dimensions. And this equation obeys the rule, which says that it is only quantities of the same dimensions that can be added. Because merely looking at this equation, we can say that, or one may wrongly assume that this equation does not obey the principle of homogeneity. You know, U plus 80. So we might say that, okay, U and 80 do not have the same dimension. But if you try to do the needful, you would see that they actually have the same dimension. So each term now, that is V, U, and 80 combined, they have the same dimension. So go and check any equation. You should try it on your own. Look at this equation. S equals to ut plus half 80 squared. You may want to try this on your own and confirm that truly S, ut, and half 80 squared, they have the same, each of them has the same dimension. You can try it out. Okay, so let us move on. So if a physical equation is represented by this, A equals to B exponential minus C minus open brackets D1 plus D2 all over E plus F. I mean, we have this question to solve. Then which statement is false? So this is an MCQ question. So the first statement is that C must be dimensionless. The second statement, you can see the third statement and the last statement. Okay, so I would suggest that you pause this video, try this on your own, then you come back to the video to see my solution. Okay, so let us try to solve the question. I still have the question with me here. So we want to, the question is, they give us A. Oh, let me leave this. Yeah. So A to be equals to B exponential minus C, then minus. So here we have D1 plus D2 over what? Over E, capital E, plus F. Okay, and now what we are planning to do is we want to check which of the statements that follow. There are 4 statements, so which of the statements must be false. Okay, so the first statement A is that C must be dimensionless. So let me just write number 1. So we are going to check if this statement is true or not. So C must be dimensionless. Now look at C, look at where C is. So before we decide if this is true or false, let me tell you something. In dimensional analysis, sign trig functions generally, trigonometric functions. So trig functions, okay, logarithms, and yes, exponential function. We have exponential function. Let's exponential x of e raised to power x. Okay, so all these, they are considered pure numbers. So, they are pure numbers, and because they are pure numbers, do not forget the other time, pure numbers are dimensionless. Yes, they don't have dimension. and you can try it out. When we say trig functions, we mean sine of something, cosine of something, tangent of something. If you press sine 30, of course, if I say sine x, now x can be any number. Okay, so if x is 30, so in degrees now, so sine 30 will be equals to 0.5. You can see that sine of something or sine of an angle will give you a number. Tangent of an angle will give you a number. Cos 30 now should give you 0.866, a number. Log of something, so maybe like log 20 or log whatever, should give you a number. Same as exponential. Exponent of anything should give you a number. Is that taking exponential 0? If x is equal to 0, x could be any number. So exponential 0, exponential 100, exponential minus 20 will give you a number. So you can see that it is actually true that trig functions, logarithms, exponential functions, they are pure numbers. And because they are pure numbers, they are dimensionless. They don't have dimension. Okay, so now coming back to this, the first option is that C must be dimensionless. Okay, that is, this C must be dimensionless. That's actually true. So if this is an exponent, it is an exponential function. So this exponential function, it does not have units. It is, sorry, not units. It does not have dimension. It is dimensionless. So for it to be true that it is dimensionless, then its argument here must be dimensionless. What am I saying? Let me try to put something here. So if I say exponential x, so since exponential function in dimensional analysis is dimensionless, it does not have dimension, so it means its argument here, x, which is the argument, must be dimensionless. Let me give you another thing. What if it's not exponential x? What if it is exponential a over b? So it means that a over b combined must be dimensionless. So if you have exponential, let's say t over y, so t over y in combined must be dimensionless. Is that taken? So okay, let me try to say something. If t is time now, t has a dimension of what? You got it right, capital T. Okay, so it means that if I give you a question, now I'm bringing out a question out of a question. If I give you a question, if I say, okay, from this question now, exponential t over y, where t is time, okay, what's the dimension of y? Okay, so since this combined, t over y, as I've said, must be dimensionless. So for this whole thing to be dimensionless, so it means y and t must do what? They must have the same dimension, so that the dimension will just cancel out. So it means this y also has a dimension of capital T, but t over y combined must be dimensionless because exponential function is dimensionless. So because of that, this c, which is an argument of the exponential, must be dimensionless. So it is true that c is dimensionless, so it's not false. Now the second thing here, let me check the second thing. The second thing here is that f, capital F, yes, this f, and maybe I should change the color of this thing for, yeah, let's just spread now. So f and this f and what? F and d plus d1 plus d2 must have the same dimension. Okay, so look at that, is this and this combined. Yes, this and this combined, they must have the same dimension. This is not true. You are asking why? I'll tell you why. So the reason is because I told you that according to the principle of homogeneity of dimension, if you have an equation A equals to B plus C plus D, So suppose this is your equation. So it means that, okay, let me add one more, plus E F, and let's say plus G over H. So for, you can see that there are several terms here and they are added together, like B plus C, C plus D, D plus EF, EF plus G over H. So each term of this equation must have the same dimensions. So before you can add any two terms together, then it means they have the same dimension. So it means that D and EF have the same dimension. But D and E, they don't have the same dimension. Is that taken? So they don't have the same dimension unless if F is just a number, maybe like 2. And they didn't tell us if F is a number or not here. So we can't just say D and E have the same dimension. So D and EF, they don't have the same dimension. Sorry, D and E, they don't have the same dimension. But D and EF combined have the same dimensions. Okay? Another thing is D and G over H have the same dimension. So it is wrong for me to say that F and D1 plus D2 have the same dimension. What is correct, or what is true, is that F and D1 plus D2 over E have the same dimension. That is, this combined and this have the same dimension. Another thing that is true is that this combined and this have the same dimension. So each term has the same dimension. So that is why statement true is, yes, this is false. Yeah, this statement is false. Now let's move on. Maybe we can, so we'll check. Let's use the next page. Okay, now for statement 3, for the third statement, we want to check if D1 and D2 have the same dimension. Yes, that is true. If you look at the equation, the equation is A equals to B exponential minus C, and I think we have D1 plus D2 over E. Is it E? Let me check. Yes, over E. Yep. And we have plus F now. Yes. So D1 and D2, you can see that we say D1 plus D2. Since we can add them together, then they have the same dimension. That is D1 and D2. D1 plus D2 have the same dimension. Okay. So, and which other thing? So this is true. So the last thing here is D1 plus D2 over E, that is this term, must have the same dimension as this. Wow, very correct. So this and this must have the same dimension. But someone will be like, but this is minus and not plus. So either addition or subtraction, it works. And also, do not forget that what is subtraction really? If I say 2 minus 3, 2 minus 3 is the same thing as 2 plus minus 3. Do you get that? So either plus or minus, like before you can add or subtract two quantities, then it must mean that they have the same dimension. And that is what principle of homogeneity of dimension tells us. So it means this last option is also true. So it's only option B that is not true. Okay, let's move on. Okay, so look at this equation. Look at this question. Now we have V to be equals to P plus 1 over N over X. Then what are the dimensions of N and X, given that V is velocity, P is pressure? Okay, so now let us start with, I would love to solve this first question, which is to find the dimension of N. Let's do that up here. So, and I'm going to use the principle of homogeneity of dimension. If you look at this formula, you can see that P plus 1 over N. Since I can add this together, then it means they have the same dimension. We are still banking on the same principle. Okay, so the principle is very important, as I've stated before. So P, that is this P, which is pressure, and 1 over N, they have the same dimension, since we can add them together. And this is how to show that. So they have the same dimension. So we can now go on by trying to find what's the dimension of pressure. Dimension of pressure. Pressure is the formula is force per unit area. So we can say pressure is force over area, right? So let me write the formula here. So we have this to be, this will span to the next page. Force over area. Okay. And this is equals to, so let's just hold on this over here. All right. So let's move on, continue on the next page. So now here we have force. Now what is force? Force, the formula for force is mass times acceleration. Okay, so force is mass times acceleration. Okay, everything over area. Area could be taken as length times breadth or whatever. We know that the unit of area is meter squared. Okay, that's SI unit. And so we move on. For this one is still 1 over n. Okay, now here, okay, let me try to rule. Okay, now come back here. What's the unit of mass? Mass is measured in kilograms. This is measured in meters per second squared, and everything over meter squared. And this is equals to, so we have 1 over n again. And so here now, the m squared can go up according to negative indices law. So that we now have kg, then we have meter per second squared, then multiply by m raised to the power minus 2, and this will be equals to, so we have 1 over n. Good. And the next thing is here, this is m raised to the power 1 multiplied by minus, that will be 1 minus 2, and we have minus 1. So this becomes kg m raised to the power minus 1 s raised to the power minus 2. Good. And this will be equals to okay, so let's say 1 over n again. Then let's proceed. What's now the dimension? Dimension of kilogram is, what is the dimension of kilogram? Yeah, that's capital M. Oh, good. Capital M. Dimension of length is capital L raised to the power minus 1. That of time is capital T raised to the power minus 2. And everything equals to, so we now have 1 over n. Alright. And here we have, so dimension of 1 over n is this. That is, dimension of 1 over n is m, l raised to the power minus 1, t raised to the power minus 2. So now to get the dimension of n, are you with me? I can say that n is, you know, this n raised to the power minus 1. Do you get it? Equals to, we have m raised to the power 1, l raised to the power minus 1, t raised to the power minus 2. And I can multiply through by minus 1, so that I now get this to be n. N will now be equals to, here m has just 1 before, so it becomes minus 1. This has minus because before, now it is now L, you know, minus 1 times minus 1, so we have plus 1, and this becomes t raised to the power 2. And voila, we are done. So this is the dimension of n. You can see that it's not hard, you just have to understand what you are doing. Now moving on to the second question, which is the dimension of x. Yes, dimension of x is the next question. So the question is, the original question is, so that we don't forget what we are solving, is v equals to square root of, I think we have p plus 1 over n and everything over x. Yes, and yes, we have found the dimension of n. Now how do we find the dimension of x? How do we do this? You know, straightforward, we just say that for the dimension of n, since pressure and 1 over n, we can add them together, so it means they have the same dimension. And since I can easily derive the dimension of pressure, it's not a problem for me, So we derived the dimension of pressure, so we take the inverse, and that gave us the dimension of n. Okay, so but for x, x is not being added to anything. Then how do we do this? I think what we should do is that we try to make x the subject of the formula here. So if we do so, then the deed is done. Okay, but how do we do that? Let's take the square of both sides. Let us simplify the equation by taking the square of both sides. And if that is done, so this becomes v squared equals to, when you take the square of this, then that cancels out the square roots. So now we have this. Okay, and now I can cross multiply. So if you cross multiply, you have v squared x to be equals to p, plus 1 over n. Okay, now here I have another expression. From this expression, I can just say that, you should agree with me, according to principle of homogeneity of dimensions, that this, like each term of this equation must have the same dimension. Yes, that's what the principle states. Okay, so I can now say, what should I use? Let's use pressure. So I can now say that, it is safe, right, and legal for me to say that the dimension of v squared x will be equal to the dimension of p. Yeah, they have the same dimension. Okay, and dimension of pressure, so we already derived it, so I don't need to go over it again. Is that picking? So, and what is v? I know v is velocity, so easily I can find dimension of velocity. So dimension of velocity will just be what? It will be meters per seconds. That is the unit of velocity first. Meters per seconds, then squared, and we have x here, right? And that will be equals to dimension of pressure. Since pressure is force over area, is that taking? And force is kilogram meters per second squared. Force times, mass times acceleration divided by area, that will be meter squared. And if it goes up, so we have multiplied by m raised to power minus 2. Okay, and here, so now we have this becomes m squared s raised to power minus 2 and x, whose dimension we are trying to find. And here, this can give us kilogram m raised to power minus 1, good, s raised to power minus 2, and here we are. So now we can divide both sides by all this so as to make x to stand alone. So I can now say x, here is my x. Okay, x is now equals to what? Yes, kg m raised to power minus 1 s raised to power minus 2. Okay, everything over m squared, all right, s raised to power minus 2. And okay, let me try to simplify this here. So this should be equal to okay, let's say it's equal to kg. So now we have m raised to power minus 1, yes, and we have s raised to power minus 2. Oh, it cannot contain here. So we have s raised to power 2. You know what? Let me rub off this place. Okay, let me just rub off this place. And use the, don't let us be lazy. Let's just do it as we ought to do it. Okay, so here now we can say, okay, this is equal to, now we have kg m raised to power minus 1. Now the m squared, if it goes up, we have m raised to power minus 2, and our s raised to power minus 2 before. So this s, but that's still, why are we stressing ourselves? This cancels out. Alright, so that we have this, and we can now say this is kg m raised to power minus 3. All right. And this is the unit of x. So what about the dimension? Dimension will just be, what is the dimension of k? G, that's m, and this is L raised to power minus 3, and where, and this is just this. This is just what we are trying to find. Yeah, that took a while, right? So I recommend that you practice over and over, because if they give you MCQ question, the time may not be enough. This kind of question, they ask you to solve it. They may not give you more than, they may not give you up to 2 minutes. Okay, and this is something that you can solve in less than 1 minute, when you practice over and over again. So let's move on. Okay, now, yes, here we have, in this question, the velocity of a transverse wave along a stretched string depends on, okay, yes, we can derive an equation. We can use dimensional analysis to derive an equation. So look at this question now. We want to find the equation or the expression that shows how velocity depends on stress, okay, density, and length. Okay. And that's what we are going to do next. Let's move on. Let's start it here. So this is what we are saying. Velocity. We want to derive an equation based on what is given. We were told that velocity depends on 3 things. We were told that it depends on P, which is stress. Okay, it depends on, what else does it depend? It depends on rho. Okay, and it depends on length. That's what it told us. But how it depends on them, we don't know. So we can now say this is proportion. Like if it's proportional to this, then if we change that proportion so that we have a constant of proportionality, which is k. Okay, so we can now say that this is p raised to power something, rho raised to power something, and L raised to power something. So it's just what we are saying. We are saying that velocity depends on this, like depends on P, stress, depends on density, depends on length, but we don't know how it depends on them. So it is now our duty to use dimensional analysis to show how velocity depends on all of this. And if you have not forgotten, this is one of the applications of dimensional analysis mentioned in the first video, that we can use it to show the exact dependence of one quantity on other fundamental quantities. Okay, so we want to, or on other quantities. Okay, so we want to show how velocity depends on these 3 quantities. Okay, right from here we can put this as x, y, and z. We don't know how it actually depends on them. We don't know if it is directly proportional, inverse proportional, but we'll get to know that using dimensional analysis. So whenever you are given something like this, you first set up this equation. Okay, this k is a constant of proportionality. Now let's move on. Let's use the next page. Okay, so just like I've written on the previous page, we have V to be equals to K, P raised to power X stress, we have rho raised to power Y, and we should have been, yes, length raised to power Z. Okay, and in doing this, what you need to do is write the dimension of each of the quantities there. What's the dimension of K? Oh, the dimension of V rather. You want to know the dimension of V, the dimension of K, the dimension of P raised to power X, the dimension of what else? Yes, of density, which is raised to power Y. You want to know the dimension of L, which is raised to power Z. Okay, and V is velocity, stands for velocity. dimension is, unit is meters per second. So the dimension is L t raised to power minus 1. And k is a pure number. It's just a number. And for a pure number, is that we say they are dimensionless. Yes, they are dimensionless, or their dimension is unity. So that is for pure number. So you should note, for pure number, like, okay, let's say 2, the dimension can be taken as, dimension of 2 can be taken as m raised to power 0, L raised to power 0, T raised to power 0, and this will give you 1. So their dimension is unity, just 1. Okay, and if dimension of this is unity, so that means this is just 1. So 1 multiplied by all of this is still the same thing. So that's how to address that. The dimension of this is stress, and stress is also force per unit area. Okay, and for force, the unit is kilogram meter per second squared over meter squared. So that should be kilogram. We found this. You may want to check, same thing as that of pressure. You may want to check what we have in the previous pages, or previous slides. So that is kilogram. Now meter over meter squared, this will give us L raised to power minus 1 and per second squared. This is T raised to power minus 2. Yes. But there is X, so let the X be here. Alright. So for density is mass over volume. So for mass, that is M, volume is L cubed. That will be L raised to power minus 3 since it's over volume. Then we have Y. You may want to check the first video for you to understand how I got this. For length, this is this is just L. So L, then here we have Z. Okay, now let's move on. So here, this is just velocity is still what? I can write velocity as m raised to power 0. M raised to power 0 is 1. So L raised to power 1, T raised to power minus 1. And this will be equal to, here, if I make use of this exponent now to multiply all of this, so we have this to be, you may want to check your indices, indices in your general math, so as for you to be able to find your way around this. The physics is not hard, the math may be somehow. So m raised to power x, so here we have L raised to power minus x, then T raised to power minus 2x. Okay, and here we have, let me open the bracket and close the bracket, and here we have m raised to power y, now L raised to power minus 3y. Okay, oh sorry, and here we have L raised to power z. Okay, and here, moving on now, here this is m raised to power x, m raised to power y. So we have, can say we have m raised to power x plus, yes, plus y, okay, we have m raised to power x plus y, and for L, we have L raised to power minus x, okay, minus x minus 3y and plus z. And which other thing do we have? For t, yes, t is just t raised to power minus 2x. Okay, and here it is m raised to power 0, L raised to power 1, T raised to power minus 1. Okay, now that we have all of this set up, so we can now yes, we can compare both sides of the equation, and if you do the comparison, so here for the m now, let's move to the next page. Let's work with the first page. Okay, no, let's work with a fresh page, but before then, yes, let's move on. So this is what we have, and just like I've said, we are going to equate the we'll compare the two sides of the equation, rather, yes, equation 1 and equation 2. So for m now, for this, so if we compare the exponents of this and this, then you should agree with me that we have x plus y to be equals to 0, and this implies that x equals to minus y. And for t, or for L, yeah, let's start with L. For L, yes, and here we have 1 to be equals to minus x minus 3y plus z. Okay, you know, this exponent of this is equals to this. And here, maybe we should try to simplify this. Since x equals to minus y, so if I put it here, then I have 1 to be equals to minus x is minus y. So that will be minus minus y. Now minus 3y. Oh, sorry. This is y. Okay, let me just erase this. Okay, minus 3y and plus z, and this implies that we have 1 to be equals to, this is plus y, so that will be y minus 3y. That should give us minus 2y plus z. All right, and for t, so for t, we compare the exponents here, this and this. Okay, so we have minus 1 to be equal to minus 2x, good, and this implies that our x will be equals to 1 over 2. Yes, if x equals to 1 over 2, if you come back here, so it means that you know, x is 1 over 2 equals to minus y now from this equation. So, and this implies that y equals to what? Minus 1 over 2. Good. So now to find z, we can use this equation. All right. So using this equation, so here we can say 1 is equals to minus 2. What is y? Y is minus 1 over 2. Okay, plus z, and this will give us what? 2 should cancel out. So now we have 1. Okay, so we can now say 1 is equals to 1. You know, minus times minus will give you plus z. So this implies that z should be equals to 1 minus 1, and that is 0. Okay, now we know that z is 0, x is 1 over 2, y is minus 1 over 2. Okay. So we go back to the very beginning, the equation that we wrote. You know, v equals to velocity equals to k, which is a constant of proportionality. Now we have p raised to power x, density raised to power y, and length raised to power z. Okay, and if we substitute these values for x, y, and z, now we have v to be equals to k. Now p raised to power x is 1 over 2, good, and rho density is minus 1 over 2, and L is raised to power 0, right? And this should give us, in indices, according to one law of indices, a raised to power 1 over 2 is same thing as square root of a. Why? a raised to power minus 1 over 2 will be 1 over square root of a. Okay, so if we apply that here, then this will be equals to k. Now this is square root of this, all right, over square root of rho. Okay, and because that's minus, to come down, and this is just 1. A raised to power 0 is 1. So we can now say that v will be equals to k, then square root of the stress, okay, over density, and this is the volume. So this is now the expression, or the equation, yes, the equation that we are asked to find. So it means the velocity, depends on, this is how it depends on these parameters, stress and the density. So you can see that L, the length is no longer there, so it means it is independent on the length. It does not depend on it. That's what it means. So this is the actual equation. Let's move on to the next question. All right, we're almost done. These are just additional problems that I think I just felt I should have them as bonus. Now, the displacement of a particle is given as this: x equals to a sine omega t. Then find the dimension of a and dimension of omega. This is what we are going to use, principle of homogeneity of dimension. Okay, x, this x stands for displacement. So this is another thing. Yes, this is sine, a trigonometric function. So sine of something. Do not forget, a trig function is dimensionless. So it means this does not have dimension. And that is, its dimension is unity 1. So it is dimensionless. So we can now say that this and this must have the same dimension. What am I saying? What I'm saying is, if you have an equation like this, A equals to B, then dimension of A must be equal to dimension of B. What if the equation is A equals to B? Now sine theta. Since sine theta is known to be dimensionless, so it still remains the same, that A and B must have the same dimension. If A equals to B plus C, A, B, C, each of them must have the same dimension according to the principle of homogeneity. So same thing happens here. So X and A will have the same dimension. So the dimension of X is L. Therefore, so A, its dimension now will be equals to L. Good. Now another thing is dimension of omega. So what we have here is sine omega t. Okay, and t, this whole thing, it can be taken the same thing as theta. Sine theta now. Theta here, theta is an angle, and angles are measured in degrees or radians. So angles, they have units, but they are dimensionless. So since theta is dimensionless, so it means omega t, because here now what we have now is that theta is equals to omega t. So it means the product of this and this must be dimensionless. T is time, so t has a dimension. So it means that the dimension of this and this must be equals to 1. That's what we are saying. If it is dimensionless, it means the dimension is unity, is 1. So, and if that will occur, it means dimension of omega and t, this whole thing, must be 1. Is that okay? So, and we know the dimension of t to be capital T. It is the dimension of omega that we need. So for us to find the dimension of omega, so we can just take it as the inverse. So I can say, so this is t, dimension of, okay, no, let's find the dimension of omega. That's what we are trying to find here. Oh, I'm sorry. Why is this thing like this? Let me try to rub this off. Okay, so let me find my pen. I'm coming. Now I found it. So now I can make omega the subject of formula. Then this must be equals to 1 over t. And that is t raised to power minus 1. The idea here is that this whole thing inside, like what we have inside, what we have as argument of this sign function must be dimensionless. I mean, its dimension must be unity 1. Okay, if it is dimensionless, the dimension is unity 1. Okay, so because sine function itself is dimensionless, if you have not forgotten, the other question that we treated the other time, we said that exponential minus c, since exponential function is dimensionless, then the argument here must be dimensionless, or its dimension must be unity. Okay, so here too, since sine function is dimensionless, whatever it is that we have inside must be dimensionless, or must have a dimension of unity, which is 1. So because of that, the dimension of this, which is the argument now, must be 1. But what is t? T is time, its dimension is t. Then if we make omega this to be a formula, then we get its dimension to be t raised to power minus 1. And if you put it back here, so t raised to power minus 1 and t, that will be t raised to power minus 1 plus 1. That gives t raised to power 0. And what is t raised to power 0? 1. Alright, so let's move on to the next question. So in this question, we are going to determine the dimension of k and omega. The dimensions of k and omega. And this question is similar to that which we solved in the previous slides. We are going to still apply the same thing that was applied over there. So here we have y. This is our equation coming. So we have y and equals to b cos omega t, no, cos kx minus omega t. Okay, and what you should not forget is the fact that this cosine is a trig function. So because it's a trig function, it is dimensionless, or we can say that its dimension is unity. That is 1. So if its dimension is unity, then its argument here, what are the arguments? Kx minus omega t must have dimension of unity. Okay, and another thing we are going to apply here is the fact that, you know, we said that if a is equals to b plus c, that is, whenever we are able to add two quantities together, I mean, whenever two quantities are added together according to principle of homogeneity, then it means those quantities have the same dimension. I mean, each of them has the same dimension. So here now that we have kx minus omega t, so it means kx and omega t, you know, some will be like, but we'll subtract, but I explained the other time that either addition or subtraction. So kx and omega t, each of them will have the same dimension. So what do I mean? What I mean is dimension of kx and dimension of omega t must be equal. Yeah, the dimension are equal. Okay, and dimension of each of them, because cosine function is dimensionless or has dimension of unity, so I can say dimension of each of these things must be equals to 1. Okay, and as we did in the previous slides, so we can now say that, so to find dimension of omega, this is what we have, this equals to 1. Now this is t stands for time. So what's the dimension of time? That is capital T. So we can say omega t is equals to 1, and this implies that omega will be equals to 1 over t, you divide both side by t. So dimension of omega is t raised to the power minus 1. We derived this in the previous slides, and permits me to do for this here, for k. For k, in the same way, so we can say kx equals to 1 as usual, and x, the dimension of x is capital L, so we can now say, I don't want to move to the previous slide, let's just manage this space that we have here. So this will be equals to 1, and this implies that the dimension of k is equals to what? Is equals to L, it will be 1 over L, and that will be L raised to the power minus 1. Alright, and okay, let's just move on. Let's move on. So to the next slide. So here we are to determine the dimension of A, B, and C, where X has the dimension of length. And trust me, this is no different from what we did in the previous slides. The two just before this. So if you look at this equation given, X equals to A cos BC plus C. So let's start with the fact that a trig function is dimensionless. It has a dimension of unity. So its argument, the dimension of each term, must be equals to 1. Is that taken? So that is dimension of BT must be equals to 1. Okay, so this must be equals to 1 like that. And the dimension of, what's the dimension of T? That's capital T. T stands for time. So we have this to be equals to 1. And if you cross multiply, then dimension of B must be equals to t raised to the power minus 1. You can see this is not hard. And another thing is dimension of C. This one, dimension of C must also be, since BT and C, we have them together according to that principle, it means they have the same dimension. And the dimension of BT is equals to 1, so it means dimension of C must be 1. What does that mean? C is dimensionless. It's just a constant. So its dimension is unity. Okay? Or we can say it is dimensionless. Now it remains A. Yes, the dimension of A from here. But do not forget that this whole thing, cos and its argument, is dimensionless. Is that taken? So because of that, dimension of X will be equals to dimension of A. Or let me try to show to you what I'm saying. So dimension of X here, if we say it is equal to dimension of what we have here, dimension of A cos cos B T plus C. Alright, and dimension of this whole thing is 1. Okay, because it is dimensionless. So we can now say dimension of X is equals to dimension of A multiplied by 1. So this is just dimension of A. But what's the dimension of X? X has dimension of length. So I can say dimension of A is equals to dimension of L. And here we are. So that's that about that. Let's move on to the next. Okay, so in this question, in a particle accelerator operating at power P, okay, P stands for power in this equation, a charged sphere of radius r and density rho, as its speed increased from u to 2u, over a distance x. So they try to define each of the parameters here. Now a student derives this equation: x equals to 28 pi r cubed u squared rho over 9p. Now show whether this formula is dimensionally consistent. If you have not forgotten, one of the things we use dimensional analysis to do is to check if an equation is dimensionally consistent, or if it is valid. Okay, so now in this equation we want to show whether this is valid. All we just need to do is to write the dimension of each of the parameters present. Okay, and we are good. So to begin with, let's start by writing the parameters of the dimension of each of the following each of the given parameters. Okay, so we write for those that are on the right hand side, and if it is equal to what we have on the left hand side, then this equation is dimensionally balanced. You know, if a, according to principle of homogeneity, if we have an equation that says a equals to b, then dimension of a must be equals to dimension of b. So that means that dimension of this x must be equal to dimension of everything that we have here. So let's use the next page to solve, so that we have a fresh page for solving. Okay, so let me try to write down the question again. And the question is x equals to, I think, 28 pi. Is it pi? Yes, 28 pi. Then we have r cubed, and there is u squared, and there is rho, right? And everything over 9p. Yes. So this is what we have here. Okay, and let's start with the dimension of x, and this is not a problem, it's just L will be equals to, now, dimension of 28 multiplied by pi r cubed, okay, u squared, and rho. Everything over, yes, dimension of 9p. Okay, and here, what's the dimension of L? That'll be x, that's L. So this should give us L, and this should be equal to, now what is the dimension of 28? 28 is just a constant, it's a pure number. So pure numbers, they are dimensionless. I would say they have dimension of unity, that's 1. So 28 pi, they are pure numbers, so their dimension is unity, which is 1. Then r is a radius, so its dimension is L. So we have r raised to power 3. Right, now u is what's u now? U, yes, u stands for velocity. So, and dimension of velocity, you do unit is meters per second. So then the dimension will be meters per second. No, sorry, L to raised to power minus 1. But there is square there, so we have squared. So the dimension of the unit of density is mass over volume, that's kilogram per meter cube. So the dimension will be capital M, and L raised to power minus 3. Good. And this is what we have here. So everything over what? Over here we have 9. So dimension of 9 is 1. It's a pure number. So dimension of pressure is force over area. And what is force? Mass times acceleration. That is kilogram meter per second squared over meter squared. And if you do the needful, we have done this in the previous slide. So we can now say the unit is kilogram, then meter cancels meter. You know, we have meter, 1 meter on top, 2 meters at the bottom. Okay, so that will be m cancels one of the m, so that the remaining meter at the bottom goes off. Check the previous slides for the dimension of pressure. So it should be kilogram per meter, then per second squared. So that should be, and for kilogram, that's capital M per meter, L raised to the power minus 1, and per second squared, T raised to the power minus 2. And this is what we have for pressure. Okay, now let's try to simplify further. So this is L, so we say it is equals to, now here we can open the bracket so that we can answer that we have L cubed, then multiply by, this will be L squared because of these two. Alright, and this one will be T raised to the power minus 2. So T raised to the power minus 2, and we have M, so that is M, L raised to the power minus 3. So everything must be equal to what? It must be equal to M. So L raised to the power minus 1 and T raised to the power minus 2. Alright. Okay, so what can happen here? Let's move on. Here we have L raised to the power 2, L raised to the power 3, L raised to the power 2. That will be L raised to the power 3 plus 2, which is 5. Then minus 3, that's L raised to the power 2. Okay, so it's L raised to the power 3 plus 2 minus 3. Okay, so you may want to check your indices in maths. So, and that should give us L raised to the power 2 in total here. L raised to the power 2, then T raised to the power minus 2, and there is M. Okay, so everything should be equals to M again, L raised to the power minus 1, then T raised to the power minus 2. So you can agree with me that this will cancel this, while this will cancel this. Okay, and this L raised to the power minus 1 can go up, so it becomes L raised to the power 1, and this gives, we have L squared multiplied by, so L raised to the power minus 1 going up becomes L. So, and you can now see that the dimension of this is now equal to this will give us L raised to the power 3. So since they are not equal, hence this is I can say this is it is this equation. So the equation is not valid. Yeah, it's not valid. It's not valid because it's not dimensionally consistent. Yeah. Oh, sorry. Dash. That should be D there. So the equation is not valid. And why is it not valid? Because it's not dimensionally consistent. Okay. So let's move on to what we have next here. So this is a multiple choice question, and you may want to pause the video and try to solve this on your own, then you come back. So which of the following statement is true? So the first statement, all quantities in mechanics are derived from 3 or 4 fundamental quantities. All quantities in mechanics are derived from 3 or 4 fundamental quantities. Yes, this is not true. It's not true because all quantities in mechanics, all quantities are derived from just 3 fundamental quantities. So they are derived from 3 and not 4. And what are the 3 fundamental quantities there? We have mass, length, and time. So this is what we have. So this is what is supposed to be true. So because of that, the 4 there flag this. So the next option there, Dimensionless physical quantities do not have units. Let's think about this. Dimensionless physical quantities, they don't have units. So it means if a physical quantity is dimensionless, then it does not have units. This is not always true. So let me give you an instance. Angles. Angles, they have units. What are the units of angle? Angles are measured in degrees or radians. So angles have units. They have unit of measurement, yet they are dimensionless. So because of this, I can say that dimensionless. So angle is a dimensionless physical quantity, but it has units. So saying that dimensionless physical quantities do not have units, this statement is not true because it is not always true. Okay, although let me give you let's talk about what should we talk about now? Let's talk about mechanical advantage. MA. Mechanical advantage does not have units because it's just ratio of force, output force to the input force. No ratio, no units. Sorry, no units, no dimensions. It's just a ratio. Now angle, but angles, like angle is an exemption now. So we saying that dimensionless physical quantities do not have units. So this is not true. It's not true because it's not always true. So I can't be so affirmative that if a physical quantity is dimensionless, then it does not have units. We have some that are true, like velocity ratio and like mechanical advantage, and I think one of them is specific gravity. So we have quite a number of them like that, but it is not all of them because we can see that angles, they have units yet dimensionless. Okay, so the next option here, the dimensions of a physical quantity are the same as its units. The dimension of a physical quantity are the same as its units. No, this is not true. We can't say the dimension of a physical quantity must be the same as the unit. No, it is not true. So, and let me give you an instance. If you look at if I ask what is the unit of energy, energy is measured in joules. Unit of energy is joules, and this is not the same as the dimension. Now the unit of work can be work is force times distance, so we can take it as Newton meter. Yes, work and energy, they have the same dimensions, but you can see that the units are different. I mean, they have different units. So work is so the units can be taken as Newton meter because it's force times distance. This is joules. Now this and this have the same units but different dimensions. Impulse is mass times velocity, and that is kilogram meters per second. Then which other thing? Oh, sorry, impulse is not mass times velocity. That's momentum. Momentum is mass times velocity, but impulse is force times time. So impulse has unit of force, that's Newton seconds. Now momentum is mass times velocity, the product of mass of a body and its velocity, kilogram meters per second. And they have, you can see that the units are different, but they have the same dimension. So this is not true. The dimension of physical quantity are not the same as its units. Okay, and now look at the last. So this is also not true. Oh, now let's check if the last option will be true. Yeah, that should be. Okay, so regardless of the units used, the dimension of a physical quantity does not change. This is true regardless of the unit. You can see here that we said that the unit of momentum is kilogram meters per second. So, but now we say that, okay, I think I shouldn't use this to explain this. Let me use this to explain this. So the unit of force, yes, unit of force, we can use Newton, or we can use, in force is mass times acceleration, we can use kilogram meters per second squared. So either we use this or we use this. Okay, so and regardless of the units that we use now, the dimension of force remains kg, that is m, l to raised power minus 2. So the unit does not affect the dimension. So regardless, we still have another thing is frequency. Yes, frequency as unit of, frequency is measured in hertz, so we can measure it in hertz. And some people will say the prefer cycles per second. All right, so either we use hertz or we use cycles per second, then the dimension of frequency remains t raised power minus 1, because cycle in the unit of frequency is dimensionless. I mean, that's the dimension of unity, so that will leave us 1 over s, and that's just t raised power minus 1. So regardless of the unit that is used, the dimension of a physical quantity does not change. And here we are, I predicted right. So D is true. So A, B, C are not true, but D is true. All right, so let's move on. So the next, so I want to give you a bonus, and what bonus is that? You should try to solve this. The question says that a book with many printing errors contains 4 formulas for the displacement y of a particle, and so these are the formulas. There are 4 formulas. So which among these formulas is or are correct? Okay, so let me just give you a hint. This is a sine function, a trig function, sine. So you know that its dimension must be unity. So dimension of this argument must be unity. So you use that to check if it is, just check their argument. So the dimension of each argument must be unity. Okay, and which other thing? So that's not the only thing to check. That's the only thing to check here. For this, check if the dimension of this is unity, and for this, check, this and this must have the same dimension. Since this is dimensionless, you can watch the previous slides to confirm what I said now. So, and you should check if the dimension of this is equal to the dimension of this, and also check if the dimension of the argument of sine here is unity. Okay, if it is going to be equal to 1. Note that T stands for velocity, V stands for, T stands for time, V is velocity, capital T is period. Okay, and another thing is, yes, here to check if this argument, if its dimension is unity, and for this you check also. So this is how to check, and yes, that's what you should check. So know if these equations are dimensional, like if they are dimensionally consistent, and that's a way to check for their validity. So what you are trying to check is, are these equations, do we have any of them that is, and this is an exercise for you, so you should try them out. If you found this lesson helpful, kindly like the video, and please do not forget to subscribe to the YouTube channel for more physics lessons like this. Share your thoughts and questions in the comment section. This is the YouTube channel. Also, you can join our Facebook page for questions, discussions, and interactions, and engage with posts and learn alongside other physics students. Always feel free to ask questions and share insights. This is the Facebook page. There's another thing going on the Facebook page, which is weekly physics challenge, and who knows, you might be the lucky winner. So thank you for listening, and I look forward to having you in my next class.